Hi, this is Dr. Emenacker. In this particular video, we're going to look at a couple of different topics. One is something called Leibniz notation. Then we're going to look at the power rule and the sum and difference rule. Leibniz. One of the two men who was primarily responsible for the development of the whole idea of calculus. He and a gentleman by the name of Newton came up with a lot of the foundational ideas for calculus. Now, what wound up happening is both of them were working with ideas with difference quotients about the same time, but they weren't in correspondence with one another. Okay, so as they were developing and writing things, they were coming up with their own ideas, each of them having similar ideas, but they wound up using different notation. Newton wound up using notation for derivatives that looked like f prime of x or y prime, the prime notation. Okay, this notation is very popular because it's easy to write, it's less expensive to print, okay, all kinds of advantages to it like that. Leibniz at about the same time was also working with difference quotients, working with slopes, and how these changes could be significant and of importance not just in mathematics, but in all kinds of applications, economics and other stuff. But Leibniz realized that these difference quotients, like what's in the box over here on the right-hand side, that should look familiar, it's actually a slope. And he wanted to employ a notation that indicated the slope nature of the computation. So he used notation dy dx, the difference in y divided by the difference or the change in the x values. You'll sometimes also see things like df dx. Remember, f is oftentimes the name of a function like f of x. So you're still looking at, well, f of x is just another way of writing the y value. So you're still looking at the notation dy dx. Or a third way that he suggested writing it is doing the change in the function with respect to x, d over dx of f of x. I will intentionally use all of these notations in future videos so that you're accustomed to seeing each of them. Okay, different notations used by different gentlemen, about the same period of time as they were coming up with ideas toward calculus. Kind of interesting because now when anything happens, if something, for example, happens in, I don't know, New York, San Francisco, Florida, it's a matter of seconds or minutes at the longest before you have that information available to you. Well, back when they were doing this, it was basically just writing and then books or letters being carried by hand, horseback, to other places. So information did not travel as quickly as it does now. So over time, both notations were accepted by people who were reading either Leibniz or were reading Newton. And when the different writings came together and they realized, oh, he's using f prime and Leibniz is using df dx. And they just decided to stick with both notations. We've already worked some with this difference quotient. You've probably found it's a rather cumbersome way to compute a derivative. There are shortcuts. Oh, good. One of those shortcuts, the first one we're going to take a look at is what is called the power rule. The power rule focuses on the power of x. It is this right here, the power of x meaning the exponent. And what this notation means, you may look at it and say it means I'm in a lot of trouble because I don't even have a number up there. Okay, well, there's -1. What this is it sets up a general pattern. And it says if you have x raised to any number, the derivative is going to be bring that exponent down, include your variable, and decrease the new exponent by a power of 1. For example, if we have something like x squared, the derivative is going to be bring the exponent out front as a coefficient, 2. decrease the exponent by 1. 2 minus 1 is 1, so we wind up with 2x to the first power. We typically don't write the 1 in the exponent. If we have something like x cubed, the derivative is going to be, okay, let's see, we bring the exponent out front as a coefficient of 3. X raised to the 3 minus 1 is 2. Oh, 3x squared. Derivative of x to the fourth, same game, 4x cubed. You may have in high school run across this process for computing derivatives. If you didn't, that's okay. That's why you're here. Over on the right-hand side here, written in red, let's take a look at a couple of examples and work through these. Okay, in the first case, we have the derivative, the d over dx, of x to the 17th power. Well, let's see, you bring the exponent out front as a coefficient. 17x, decrease the exponent by 1. Oh, that means subtract 1. 17 minus 1 is 16. So it's 17x to the 16th power. Well, that's a whole lot easier than doing that with the difference quotient. How about this one? Imagine you had to take x plus h to the 138th power. That would take a while. Well, the beauty of the power rule is you can look at it. The 138 winds up being the coefficient out front. We have the variable x raised to 1 power less, 137th power. And it's just that easy. This same rule applies if you have situations where you have the variable involved with a radical. So for example, the cube root of x to the fifth. Well, the first thing we're going to do here is we're going to rewrite this as an exponent with a rational, or as a variable with a rational exponent. So it's going to become x to the 5/3. It's to the fifth power and the third root. Now, to take the derivative of this, you take whatever the exponent is, you bring it out front. The 5/3 now becomes a coefficient. We have 5/3 x. Then you take the exponent, 5/3, and subtract 1. Well, 5/3 minus 1 is really the same thing as 5/3 minus 3/3. Oh, that gives us our 2/3 there. Okay. All right, so that's got that taken care of. Let's try another one of these. If you have 3 over x to the 7th, that can be written as 3 times x to the negative 7th power. Remember, the negative in the exponent just means that that variable was originally in the denominator. Okay, so if we take the derivative of that, we're going to have the 3 times the x, but the 7 also comes out front as part of the coefficient. So we have 3 times negative 7. Oh, that's a negative 21. X, then you have a minus 7 minus 1. Oh, that's going to be a minus 8. And here's your derivative. It can get a little more complicated. Let's say we have something like this one right here. We have 5 divided by the cube root of x squared. Well, we can rewrite that as 5 times x. The power is 2, the root is 3, giving us 2/3. Because the variable was originally in the denominator, the exponent winds up with a negative sign on it right there. So all we've done is to rewrite it, just like we were practicing in section R5, I believe it was. Okay. Then to take the derivative of this, all we're going to do is we're going to take the 5 times the exponent, the negative 2/3. And remember, 5 is the same thing as 5 over 1. And when you multiply these, 5 times the negative 2 is a negative 10. 1 times 3 is 3. Oh, there's our coefficient. Then, to get the new exponent, you just take a minus 2/3 minus 1. Well, wait a minute. Minus 1 is the same as minus 3 over 3, which is going to give us to the negative 5/3 power. I think you can see you're going to get some practice working with adding and subtracting fractions here, aren't you? Okay, now, What if we have something like the derivative of a constant, like the derivative of 14? Well, let's first consider graphing y equals 14. We talked about this back in the review section. The y value is going to be 14 regardless what the x value is. It gives us a horizontal line. If you have a horizontal line, the slope is 0. Oh, yeah, that's what we got over here. Remember, the derivative is the slope is 0. But numerically, how do you come up with that? Well, you can write 14 as 14 times x to the 0 power. Remember, x to the 0 power is just a fancy way of saying 1. So in this equation here on the left, I really just have 14 times 1, which is just 14. But writing it in this format allows me to then use the power rule. I'm going to bring the exponent times the coefficient. Oh, so I have the 14 times the 0. Then I'm going to have my variable x. And then I'm going to subtract 1 from the exponent. So that's going to give me a negative 1. Really doesn't matter what this exponent is because I got 14 times 0, which is 0. And 0 times anything, ta-da, there you go. There's your slope of 0. Be aware that constants, the slope of any constant is 0, as we just talked about. It's a horizontal line. But also be aware that constants come in a lot of different forms. The square root of pi is just a number. It's a constant. If you take the derivative of that, it's going to be 0. Okay. All right. So there we have a couple situations where you've seen the derivative of a constant is 0. Okay. Let's take a look at something else going on here. If we have a function like g of x equals 7x to the fourth, remember, just a quick review here, we're going to have our coefficient of 7 times our exponent 4 times x raised to, we decrease the exponent by 1, we get 3. It's going to give us 28x cubed. Okay, well that's fine. In the next example though, we've got several terms being added together. Well, the good news is, just like there is a power rule, there is what is called a sum difference rule. And basically all this says is if you have something like a function plus or minus another function, and you're taking a derivative of all this stuff at once, all you do is you take the derivative of the first function, whatever it is, plus or minus, that means adding or subtracting the derivative of the second function. Which brings us to this example right here. We have a first function plus a second function. The first thing I'm going to do is I'm going to rewrite these here. I haven't done a derivative or anything yet. I've just rewritten it so that I now have everything with an exponent. Okay, now that I have an exponent, what I'm going to do is I'm going to take the derivative of each term one at a time. The derivative of this first term is this. We have the 3 times whatever the exponent is, negative 1, times x raised to the negative 1 minus 1, that's a negative 2. Okay, that is going to wind up giving us a minus 3x to the negative 2. Then when we do the derivative of the second term, okay, and remember we're adding it, so we're going to continue to add over here. When we do the derivative of the second term, the coefficient is going to be what was the exponent, so it's going to be a 1/2 x. 1/2 minus 1 is to the negative 1/2. The good news is, adding or subtracting, you just do each piece individually and go from there. Let's take a look at another example. something a little bit more involved. It involves three terms. The first term, the 4x, that's good to go. That's 4x to the first power. The second term, 3 over the 7th root of x, I'm going to rewrite that. That's going to become a minus 3x raised to the first power with a 7th root. So it's going to be a negative 1 divided by 7. The third term continues to be x to the 4/5. When we do the derivative, you just take it one term at a time. The derivative of the first term is just going to be the 4 times the exponent of 1, x raised to the 1 minus 1. Oh, that's x to the 0 power, so the x just becomes a 1. So this is going to give us, when it's simplified, a 4. The second term, when we take its derivative, is going to be a negative 3 times this negative 1/7. Then I've got the exponent, negative 1/7 minus 1. So that's a negative 1/7 minus 7/7, which gives us an exponent of negative 8/7. Okay, so we multiply all this stuff together and we get a minus 3 times a minus 7 gives us plus 3/7 x to the negative 8/7. The third term, just going to bring the 4/5 out front. X, subtract 1 from the 4/5 gives us a negative 1/5, and there you have it. Okay, well this is all well and good. It's cute. We can do derivatives. You're getting the hang of it. You'll have the opportunity to practice more in the homework. What do we do if we have something like this? We've got this equation, and what this equation does is it tells us the total miles that have been traveled after driving for t hours. Okay, so what comes out of this function is going to be in terms of miles. What goes into this function is how many hours have we been driving. Notice for this function, we've limited ourselves to just a 4-hour trip. A first question that would be a fair one to ask is to estimate the total distance traveled in the first 2 hours. Well, to get the distance traveled in the first 2 hours, we just take the function as it is, substitute 2 in every place there's a t, and work it out on the calculator. What this says is, in the first 2 hours, we've gone basically 130 miles. Well, that makes sense. That's about 65 miles an hour, so that's reasonable on an expressway. Okay, notice we put down 129.06, and real important, I put a unit on it, miles, because this function tells us how many miles we've gone. A number without a description is not useful at all. If I just come up to you and say 17, that doesn't mean much of anything to you. If, on the other hand, I say, hey, there's $17 laying on the floor. Did you drop that? Oh, well, yeah, I guess I did. Okay, the 17 now means something. Okay, a second question that can be answered is, suppose you're asked to estimate the velocity, the speed of the car at 2 hours. Now, remember here, speed is measured, well, like on your speedometer, miles per hour. Okay. If we look at taking the derivative of this function, df dt, remember it's not dx because the variable in this case is t. If we take the derivative, what we have is the change in f, the function is measured in miles, divided by the change in time, the time is measured in hours. What you wind up with is a unit that looks like miles per hour. Oh, that's speed, not actually velocity. It's speed, which is what you get on a speedometer. Okay, so if you're asked to compute the velocity at 2 hours, What you first want to do is to get an equation that will estimate velocity. Well, that's the derivative. When we take the derivative of this function, the function up at the top, what's going to wind up happening is we're going to have from the first term the 1.91 times the exponent of 3, t squared. The second term is going to be the 17.43 times whatever the exponent was, 2. The third term is going to be the 91.75 times whatever the exponent was, 1. Then for each of these variables, the exponent on the variable is decreased by 1. When you multiply things out, you get the equation here that's represented on what you see now as the second line. When you wind up computing the speed at 2 hours, you take the derivative and you evaluate it at 2. In other words, every place there's a t, you plug in a 2. When you plug in the 2, you then can crank it through your calculator, and you wind up with the derivative has a value of 44.95, which is saying that at exactly 2 hours, the velocity of the car is 44.95. Here's where the important part comes in, miles per hour. So the units are in miles per hour. And it's very important for you to include that. If I just came up to you and said 44.95 or 44.95, you might think it's the price of something and not realize it's the speed of a car at a specific point in a trip. With these derivatives, a very important thing that we can do is we can use the derivative to get the slope of a tangent line at a specific point. For example, let's take the function of minus x cubed plus 6x squared. If you graph that, you'll get something that kind of looks like what we have here in red. Okay. Real fair question, either in the homework or on upcoming quizzes and tests, would be compute the equation of the line tangent to this function at, and give you some specific point. For example, at x equals 5. Now, the first thing you need to do is you need to figure out what are the coordinates of that location. Well, we have the x value is 5. Where did the y value come from? It's the negative of 5 cubed plus 6 times 5 squared. When you work that out, let's see here. We're going to have a negative 125 plus, that looks like 150. That gives us a y value there of 25. Aha! So the x value is 5 and the y value is 25. So that's where the 25 comes from. We're going to need that in a minute. Okay? We have an x value, we have a y value at the point we're interested in. We're asked to compute the tangent line. Well, to get a tangent line, remember, we're working with the equation y equals mx plus b. Handy to write that down because it gives me a shopping list. I need to compute a value for m, the slope. I need to compute a value for b, the y-intercept. Well, let's first go after the slope. The slope is the derivative. We've talked about that several times, and I will continue to talk about that. It's important for you to realize that derivatives are slopes. If we take our original function, this x cubed minus 6x squared, okay, and we do the derivative of that, we're going to get 3x squared negative 3x squared plus 12x. So there's the derivative. Okay, so we've got that. Then what we want to do is we want to compute the slope at a specific location. Here we are. The slope at a specific location, that location is x equals 5. So all I do is I substitute x equals 5 into the derivative. So I have a minus 3 times 5 squared plus 12 times 5. So again, negative 75 plus 60. This gives us then a value for the slope being a negative 15. Okay, so I reference once again, what am I trying to build? I'm trying to build an equation y equals mx plus b. At this point, I have a value for y. I computed that earlier, okay, up here. My y is equal to 25. I'll plug that in for y. I have a value for the slope. Well, I just computed that, negative 15. Plug that in there. We were given the value for x that we want to work with, 5 plus b. You can at this point solve for b. You get b equals 100. Now, look what we have. Here we have the slope of 15. Here we have b is 100. All we got to do is plug those into y equals mx plus b over here, and we get the equation of the line tangent to our function at the point 525. Okay? Be sure that you're able to do these equations of tangent lines. These are going to be very important for us as we move into economic applications. Let's take a look at one more example here. Okay, I made something up. I raise cattle. Let's say this is the weight gain on a calf for the first year. Now, I kind of messed up. I really should have had something like 0.085 t cubed, but I left out the zero. Here it is. We'll work with it. This isn't going to be completely accurate, but applying it is going to work just fine. First question, or first thing to notice is, in this case, I've said, hey, this equation only applies for months 0 to 12. In other words, the first 12 months. First question, well, what's the weight of a calf when it's born? Well, at birth, that's 0 months. You just plug 0 into your function, and you get 45. A second question could be, okay, what's the change in weight at month 6? In other words, as the calf goes from the 6th month to the 7th month. When you're given this time, what we want to know is how far are things going to progress in one more step from month 6 to month 7. Okay, so what we're going to do here is we're going to look at the change in weight. Oh, change means compute the derivative. When I compute the derivative of this function, first recall, oh, kind of overshot that, didn't I? When I compute the derivative of this function, remember that the derivative of the 45 is going to be 0. We're going to use the sum difference rule here that says, hey, you just take these things one term at a time and write them down, being added or subtracted, whatever's appropriate. I could have put down the derivative of 45 as 0, then I would have had 0 plus. Nobody really does that, so I left the 0 off. The derivative of this first term is 1.7. The derivative of this second term is a negative 0.0062. The derivative of the third term is 2.55 t squared. Okay, so that gives us our three terms, adding and subtracting appropriately, just like is suggested in the sum difference rule. Now, I'm asked to determine the change at a specific point in time, month 6. So what that says is I want to take the derivative and evaluate the derivative at t equals 6. So I'm just going to take the 6 and I'm going to plug it into my derivative. Crunch it out on the calculator, and what I wind up with is this number here, which is too big. Okay, I'll be honest with you, that's too big. I wish I had that kind of weight gain on the animals at month 6. But let's not worry about the number being off. Let's just take the number and say, okay, we've got a number. We need to get some units on it. so that there's some understanding of what does this number really say. Well, remember, using Leibniz notation, this would be dw dt, not dx, because here the variable is t for time. In the numerator, the weight, W, is measured in pounds. So the units in the numerator are going to be pounds. In the denominator, the variable T is measured in months. So the units in the denominator are going to be month. When you take those two and combine them, the units on the number are going to be pounds per month. This would mean from month 6 to month 7, the animal picks up 93.46 pounds in weight. Obviously, that's too much. Okay, but it's an equation. It's something to run with. We are going to continue to work with developing and identifying the units on these numbers through a lot of problems. Okay, remember, it's not all that horrible to figure it out. You just go back to the Leibniz notation and apply the appropriate units in the numerator and the denominator, and that will give you the units on whatever number you get in the derivative.